Okay, we're looking at practice question set 2B in preparation for quiz 2 on Monday. The first question, the info box says, at the starting gate of a downhill ski race, the skier pushes with his arms and legs to get as fast a start as possible. The skier leaves the starting gate with an initial speed of 1.6 meters per second. The race course is made up of both steep and flat sections. It goes on to describe the steep section and the flat section. The question says, the magnitude of the impulse on the skier as he leaves the starting gate. We will often see multiple paragraphs of information, sometimes a full page of information, the vast majority of which is not relevant to the question. Tell me what paragraph here is not relevant to this question. Paragraph 1 or paragraph 2? Which one isn't relevant? 2. That's 2. Like, yeah, that's true. The mass isn't 2, and we do need that mass. But other than that, like the rest of it's irrelevant. Like it feels like there should be another question here, right? That relates to information paragraph 2, but there isn't. That happens a lot. We often see data that doesn't matter in words and paragraphs that don't matter. This is what we care about here. Paragraph number 1. The magnitude of the impulse on the skier as he leaves the starting gate is what? What are the 2 impulse equations that I'm allowed to use? They come from splitting up one on our data sheet. Yeah. Good. Delta P is equal to M times delta V. Good. And what's the other one? Great from our data sheet, right? Yeah. Let's just say delta P is equal to F times T. And then, Jacob, we could combine them. F times delta T is equal to M times delta V, right? If you think you know which one to use it. You can't go wrong, really, because they're both valid. If you're not sure, in my experience, this one ends up being used a little bit more often. So if you're not sure which one to try, probably try that one first, okay? I think that one's going to work here because we have M and we have V. So it looks like that's the one we're going to use. Mass is 68.2 kilograms. Somebody said that came from the second paragraph. You're right. That's the only thing we need from the second paragraph. What's delta V? What's VF? 1.6. VF is 1.6. That can be a little bit confusing because it says the initial speed of the skier is 1.6. But what you got to recognize here is not so much the wording of it, but what's really happening here. Like the skier leaves the starting gate at 1.6. We're not analyzing the trip down the hill. That would be the initial speed for the trip down the hill. But that's the final speed for leaving the starting gate, right? What is the initial speed at the starting gate? 0. 1.6 minus 0. When we do that math, it works out to be A, 1.09 times 10 to the 2 Newton seconds. What's the other set of units that could have been used here?
Kilograms times meters.
Yeah, good. Kilograms times meters per second. So the answer is A. Now, we're going to skip that second question because it's a tough one. We'll come back to that. Let's go straight to the last question right now, which relates to what we learned about yesterday, the whole predetermined impulse thing and the whole non-predetermined impulse thing. Let's spend just a couple minutes reviewing that, what we did yesterday, and then we'll do this question here. Predetermined impulse occurs when an object is, go ahead, Nicole. Stopping, yeah. This is when an object is stopping. Non-predetermined impulse occurs when an object is, yeah, starting. Doesn't mean that it's starting from rest. A golf ball certainly starts from rest, but a baseball is starting not from rest, but starting from the opposite direction. Doesn't really matter. When it's starting, it's a non-predetermined impulse. When we have a predetermined impulse, it's force and time that affect each other. The impulse isn't affected by either one. The impulse is determined by the object's mass and how fast it was going. When a car stops, it's going to experience the same impulse no matter how it stops. When you jump off the desk, you're going to experience the same impulse no matter how you stop. If you can increase the time, you will decrease the force. If you decrease the time, you will increase the force. They affect each other. They do not affect impulse. Increase time, decrease force, cushions the blow, cushions an impact. Neither one of them affect impulse, though. Look at the non-predetermined impulse. The same equation applies here, but this time, force and time don't affect each other. Rather, force affects impulse. Increase force, increase impulse. Increase time of contact, good form, right? Follow through when you're swinging the golf club. Increase the time of contact. You're going to increase the impulse of the ball. So F and T don't affect each other. Okay? F affects impulse. T affects impulse. In the first situation, F and T affected each other, and neither one of them affected impulse. What do we got here in question number 2? Rock climber falls and is safe from injuries by climbing rope that is slightly elastic. What are we dealing with here, the predetermined or the non-predetermined? This rock climber falls and stops. That's a predetermined impulse, right? Whether the rock climber hits the ground or is stopped by the elastic rope, his or her impulse will be the same. What does the elastic rope do? Told you yesterday, you're going to see this question on a test, right? In one form or another. Anything that cushions an impact, including an elastic rope. Nick, anything that cushions an impact is going to do what? Increase the time. Which does what to force? Decreases the force. So my answer for that one is A. Remember I told you yesterday, you're going to see a question where we have an impact cushioning thing. Maybe it's an airbag, maybe it's an elastic rope, whatever it is, doesn't matter. If it cushions an impact, the answer is same impulse, increase time, decrease force. Okay, you're going to see that on the unit test, probably going to see it on your diploma exam as well, although we won't know until January for sure about that. Okay, last question. This is the tough one, I thought. Says a full draw is the maximum distance that an archer can pull back an arrow using a recurve bow shown below. A particular archer requires an average force of 130 newtons, full draw of 70 centimeters. We got a mass here in grams as well. Be careful with that. Circle these things, draw attention so that we don't forget to convert units. It's a hard question. It's a hard question. If you get through the bulk of the question correctly, you don't want to lose your mark on this because you forgot to convert a unit. Silly mistake like that. What are we looking for? The impulse that the bow gives to the arrow. Remember my two equations, right? Delta P is equal to M times delta V, and delta P is equal to F times delta T, right? You guys have a preference which one we try? By the way, we could combine these as well if we wanted to, right? Ft is equal to M times delta V. You guys have a preference which one you try? Yeah, I'm probably going to go with the first one. I have a gut feeling on that. If you don't have a gut feeling, then I'd probably go with the first one anyway because, I don't know, anecdotally, I find it works a little bit more often than the other one. Look, in the end, for both equations, we have one variable and not the other. Nothing jumps out as being the obvious one to use, but I'm going to try that first one. I know what M is. It's 20.6 grams, although I got to convert that to kilograms. How do you find, well, VI is easy, right? VI is 0. How do you find VF? Holy cow, Jacob is on fire in the last couple of days, eh? Okay, go ahead.
A equals force divided by mass.
Okay, you can do that. F is equal to M times A. We know what F is. Okay, we know what M is. We can solve for A. Okay, so then what? Okay. And then you would solve for VF, and then you sub that back into there. VI is 0, so whatever that is minus 0. Get our answer, right? The answer is 1.94 by the way. Good? Good. If you did it that way, which physics principle would you, on the back wall there, or the bottom left-hand corner of your data sheet, which physics principle would you say that you used if you did it Jacob's way? We've only looked at two of them so far, right? 0 and 1. Principle 0, uniform motion. Principle 1, accelerated motion. It's principle 1, accelerated motion, right? Okay. Good, good. Excellent, Jacob. Okay, what if we want to do it differently? That's not the way I did it. It's just as good as my way, but it's just not the way I did it. Anybody have another way of finding, a physics 20 way of finding, well, that was kind of physics 20 as well, right? Another physics 20 way of finding VF here? Anna? Okay. Force times distance gives you EK. Force times distance gives you work, right? Yeah. Okay. And work is equal to change in energy, right? Yeah. By the way, we're dropping, remember the cos theta on the end of that? We're dropping the cos theta because it's moving the same way as the force. So the angle is 0. Yeah, so it becomes, cos theta becomes 1. The equation becomes F times D. This part of the equation is known as the work energy theorem. That's a physics 20 thing, but it's one of those things that might rear up the odd time in physics 30. The work energy theorem. W is equal to delta E. Now, it's also equal to F times D. Here we know, when we look at change in energy, we're going to look at the change in one type of energy here, specifically kinetic. Why are we picking kinetic to go with here? Like in the end, what's the change in energy? 0. Because the elastic potential gets converted to kinetic and the total change is 0. But there is a change in specifically one type of energy, kinetic energy. The final kinetic energy is 1 F mv squared. The initial kinetic energy, as it's just waiting to be fired, is 0. Why did I choose to analyze the change in kinetic energy versus the change in elastic potential? Yeah. It's speed. That's what I'm looking for, right? Kinetic energy is the one that's going to introduce speed into the mix. It's going to allow me to solve for VF here. Okay, we solve for VF there, whatever it works out to be. Sub it back into VF minus VI here, and guess what we end up with? Same thing as Jacob ended up with, 1.94 using the other equation. Now, if I did it that way, which physics principle would I say that I used? Look at the back list, or take a look at your list in the bottom left-hand corner of your data sheet. Which principle is it? That's principle 3. Now, listen carefully, guys. You've either did this question Jacob's way, or who was it? Who was it that actually gave me? Okay, Anna. You've either done it Jacob's way or Anna's way, right? You can, if they asked you which principle you used, which principles you used, you couldn't say you used principle 1 and principle 3. Because you didn't do both, right? You used either principle 1 or principle 3. Okay, so it's okay to use, to list either one of those, and accept either one of those as answers. But in the case of being more than one principle being used, you wouldn't say 1 and 3, because you didn't do both, right? You did 1 or you did the other, but not both. So it's principle 1 or it's principle 3.